Okay, so again, we're going to talk about vectors. So they have direction and magnitude. So they look like rays. Remember back in geometry where you had like an initial starting point, right? And then you had this arrowhead, right? So the arrow on a vector just represents its direction, okay? So a vector has direction and it has magnitude. Now we're going to kind of look at all the different pieces of it and define those pieces, okay? So let's draw a vector. So you're going to have 2 points there, and we're going to just kind of go like that. So P and Q, we're going to label this. And then you might also see something like a bolded lowercase cursive letter. Okay, so you could see that on a vector as well. So to name a vector, you can choose to do one of two things. You can call it vector PQ, so you have the P and the Q, and then you have just that arrow over top. Now, the book uses a full arrowhead, but you might also see it like this, where you just have like half. Okay? So that kind of distinguishes the fact that this is a vector versus array in geometry. So this is how we write array in geometry as well. So that can distinguish it, but either is acceptable for us. And then you could also see just that bolded letter. Okay? It's lowercase, it's usually in cursive. So this is called vector PQ or vector U. Okay, so this is how it's named. Magnitude is the length of it. Okay, so it's the length of the vector. Now, you're going to use the symbol for magnitude. It's like a double absolute value bar. Okay, so this is the magnitude of vector PQ, or you could see like the magnitude of U. Okay, so that represents magnitude. That's a symbol you use. So the direction of a vector is denoted by an angle. Equivalent vectors. So in order for vectors to be equivalent, two things have to be true. They have to have the same magnitude and the same direction. Yes? Angle. It's like an angle measure. Okay, so in order for equivalent vectors to exist, they have to have the same distance or the same magnitude and then the same direction. They have to go at the same directional angle. Okay, to show that these are equivalent vectors, you're going to do two things. You're going to basically use the distance formula. Okay, and then you're also going to show that they have the same slope. So if you can show both of those things are the same, then you know that the vectors are equivalent. Okay, then there's standard position. So it's the initial point when the initial point is at the origin. Okay, so that's considered standard position, is when you start at the origin. Okay, vectors can be written in component form. Over the next couple of days, we're going to talk about the different forms that we could see vectors in. Okay, and one of them is component form, and it looks like this. It's like a set of arrowheads kind of locking it in, like parentheses would work, okay? And then you have some horizontal, comma, some vertical component, okay? So, for example, it might look like 3, 2, okay? So that's the vector 3, 2 in component form. Okay, so you ready to try some stuff with this? Now that we've defined a bunch of stuff, let's see what it kind of all looks like together. So let's call this example 1. Let's just say find the magnitude. We'll do that first. Okay, of the given vector. Okay, so we're going to start out with this vector u. And we're going to be given points, -1, 2, and 2, 3. Okay? So now anytime that you're going to find the magnitude, you want the vector, you want to see the horizontal and the vertical component. Okay? So we're looking really for like the distance. Okay, the horizontal distance and the vertical distance. We're going to write it in component form. So you can calculate this mathematically, okay, or you can count. Okay, it's pretty simple. So let's think about this. If I want to know this horizontal distance here, can I just take 2 and subtract -1 to figure out the distance? Or just count the distance from -1 to 2? Okay. And then to figure out the vertical distance, I can count from 2 to 3, or just take 3 and subtract 2. And either way, you're going to get 3, 1. So this is our vector u in component form. This is saying you have a horizontal component of 3. Okay, so the distance is 3 horizontally and then 1 vertically. Okay, now think about this. If I wanted to find the magnitude of this, okay, so I want to find the length. I'm essentially finding the distance, right? The length is just the distance formula. So that's really what I'm doing when I'm calculating magnitude. So to find the magnitude, all you have to do is the distance formula, but we've already done part of the distance formula. If you remember the distance formula, it's the square root of x1 minus x2 squared plus y1 minus y2 squared, right? Yes? Yeah, come on, go back to geometry a little while longer. Now, we've already done all the subtractions. So all I really have to do is take the square root of this and square those terms and add them together. So that's how you find magnitude. Okay? If you're given component form, you just take those two components, square them, add them together. So we get the square root of 10. Now for your final answer, you're going to write it with a proper notation. So we're going to have the magnitude of u equals the square root of 10. All the magnitude is distance formula. Square root of x1 minus x2 squared plus y1 minus y2 squared. Okay, everybody okay with finding magnitude? Pretty easy. Okay, we're going to have a few more terms we got to keep talking about. So now let's define the zero vector. Okay, now the zero vector is a vector that has no direction and no magnitude. So the zero vector just looks like this, 0, 0. Kind of makes sense. Okay, and then we come to the unit vector. So a unit vector is a vector that has a magnitude, and keep in mind magnitude is just length, of 1. That should be enough terms to get us through today. Okay, so now we're just going to try some vector operations, okay, both algebraically and geometrically. So we'll just call this example 2. We're going to practice some vector operations, but we're going to do them algebraically first. Okay, so given these vectors, -2, 3, and vector v is 4, 1. Okay, so these vectors have been given in component form. We don't have to find them ourselves. They've been given that way. Okay, if I want to do, let's call this A, I guess. If I want to do u plus v, what do you think you do? This isn't a trick question. Yeah, what do you think you might add together? Yeah, the x. okay, we are thinking of it like x's and y's. It's kind of like that, right? We're going to add the horizontal components. We're going to add the vertical components. That's literally all it is, okay? So we're going to show our work like this, and I know it's kind of silly to show your work, but we're still going to do it. So we have negative 2 plus 4, comma, 3 plus 1. So u plus v is 2, comma, 4. Pretty easy, okay? What do you think you would do if you had 2u? What do you think that means? Yeah, multiply everything by 2. This is called a scalar multiplier. Okay, that's called a scalar multiplier. So it's just a number. This is basically saying double the length of u, isn't it? Right? So what you're going to do is you're going to take vector u and you're going to multiply both of its components by 2. So 2u is equal to negative 4, 6. Notice I am using notation, right? I want to show my reader whatever I'm calculating there. So make sure you label those pieces. Okay, what would you do if it said u minus v? Subtract the horizontal components. Okay, what would you do if it said 2u minus v? Let's just do that one. Let's just say it said 2u minus v. What should you do there? Yeah, it's like order of operations, same deal. So we're going to double 2u first. Well, don't I already know 2u? Right, I calculated it in b. So you're going to multiply 2 by u. I've done that. And now I'm just going to subtract v. So I'm going to have negative 4 minus 4, comma, 6 minus 1. So 2u minus v is negative 8, 5. Okay? So maybe make yourself a note here, 2u we already calculated. Okay? Any questions on the algebraic operations? Isn't this like a breath of fresh air compared to chapter 5? So nice, right? Okay, example 3. We're going to shift gears now. We're going to do vector operations still, but now we're going to move into them geometrically. So basically just going to look at some pictures now. Okay, we're going to think about what that really means to do to these vectors. Okay, yeah?
So when you're in component form, is it just like the horizontal and the vertical are the 2 components inside?
Yep, that's all it is. Okay, so let's start out with this. So I'm going to give you, this is u, and this is v. Okay, so we're given this picture, this situation. Now, notice we don't have any components here. We don't know exactly their exact locations. We do know they're in standard position because we can see that they're starting at the origin, right? Because that's what that means. We see the initial side here is at the origin, and then these are the terminal sides. The terminal sides are the arrows. The initial side is that starting point, that end point, okay? So we're given this. If I want to find 2u now, think about what that means, okay? Doesn't it mean just to double u, double the magnitude? So what I'm going to do is I'm going to start out with vector u. And so just try to, copy it down like it was. And so this is u. And now what happens is I just double the length of it. So it's still going in the same direction, except now it's just going to be double the length. So shouldn't it look like this? So this whole piece now is 2u. Okay, so maybe make yourself a note, twice as long, but same direction maybe. Okay, everybody okay with that one? Let's try another one. Let's try u plus v. So really, you don't even have to show u. You could just show 2u. I wanted to show you, though, it overlapping so you could see it. Okay, so the pink piece is our answer. Okay? U plus v. So now what you're going to do is you're going to draw u. Okay? So you start with u, because that's what's listed first. So I start with u. And now I'm going to add v to it. So when I add v to it, I have to start here now. So the terminal side of u is now going to become my initial side of v. And then I draw v, how it's shown. So v is like this. Okay, so there's u plus the v. Now that's still not my answer, okay? Now I have to connect them. So you connect the initial to the terminal side. So this right here is u plus v. So make yourself a note here. Vectors must be initial to terminal side. Okay? Or sometimes you might hear it referred to as like head to tail. Okay? So this is the head, the beginning, and then the tail is where your arrow is at. Okay? So everybody okay with u plus v? Any questions? Okay. How about, I'm going to turn this, but you have this in front of you. So, okay. How about negative v? What do you think that means? The opposite direction. So now all you're doing is switching directions. So the magnitude's not going to change. You're just going to change the direction that it goes. So originally, v looked like this. Okay? So then negative v is going to have the same length. It's just going to go in the opposite direction. So you're just going to extend it this way instead. And, I mean, mine have different lengths because I wasn't being careful, but they should be the same length. Okay? All right? All this means is the opposite direction. Okay. Now the last one is sometimes difficult for students. It's actually kind of difficult for me, so I make it easier. So subtraction I can never remember, like the rules of it. There's different rules. You connect head to head. You can look in the book if you're curious. But for me, you can think of subtraction just like adding the opposite, can't you? And for me, that's so much easier. So I'm going to change this. Anytime I see subtraction, I'm going to think about it like u plus a negative v. Okay, because that's the same thing. And that's so much easier for me to think about. Okay, so now I'm going to draw this. So I start with u. Okay, so u is first. And now I have to add a negative v. So I know I have to go from here and I have to add a negative v. Now normally v would go out this way, right? But I'm adding the opposite of v. So really I have to go out this way. This is like my negative v. Okay, and then this, remember the rules of addition, you have to connect initial to terminal sides. So this right here becomes u plus a negative v, or u minus v. Okay, if you don't like that method, you can look up the other one in the book, but personally I think this one's easier to remember. All right. So you have to connect from the initial side of u to the terminal side of negative v. Okay? Yeah.
So is that where we test your grade or something like that? Like, you would be looking for it to touch that side? Because I guess what I'm saying is, like, when I did it, it didn't touch, so it would...
Are you saying because it's touching this right here?
Yeah.
Mine might not be drawn as accurately as yours or vice versa. Okay? If we were going to do this properly, we would have like a protractor and a ruler out. We're just kind of eyeballing stuff right now. Yeah. No, it's going to be this basic. We're talking vectors real basic this time, you guys. We're not going into this any more than this. Okay? So this is about as complicated as that part's going to get. All right? Okay, so I'm going to switch forms now. So I told you there's other forms. Now we're going to go into the next form. So that was component form. Now we're going to go into linear combination form. Okay, so linear combination looks like this. V equals A times little I plus B times little j. This I and j represent the horizontal component and the vertical component. So this is the horizontal, and this is the vertical component. So when you write your vector in linear combination form, you're always going to have an I and a J in that form. Okay? So the only thing that's going to change is the A and the B. All right? So we're going to look at an example of this. It's kind of like this. So if you think about like the X and the Y axis, for example, it's like here are all your little I's, right? You're counting by I here. That's all. This is like your J's, okay? Just like X and Y axis, okay? We just call it I and J, all right? So if I said V equals 3I plus 2J, then think about what this vector would look like, okay? So if you think about your axis, it would be like 3 along the horizontal component and then up 2. So it would end there and start in standard position. So this would be vector V because it has a horizontal distance of 3 and a vertical distance of 2, okay? What would it look like in component form? Would it just be 3, 2 with some arrowheads, right? That's all it is. These are interchangeable. They're just 2 different forms. So don't get confused if you see it either way. Everybody okay? Any questions? Keeping it going here. We talked about the unit vector. We defined it. We said that the vector has a magnitude of 1 or a length of 1. So now we're going to look at how to actually calculate it. So I'm just going to turn the page here. So the unit vector, in order to calculate it, you are going to take 1 over the magnitude of V and multiply it as a scalar through your components. This is going to force this vector to now have a length of 1. Okay, so we're going to do a couple examples of this. So I think we're on example 4. Find a unit vector in the direction of vector V if V is equal to 3I, whoopsie, there's no comma there, plus 4J. Now remember, this is the same as if I had 3, 4. Right? They're the same thing, just 2 different forms. This is component form, this is linear combination form. They mean the same thing. Go 3 horizontally, 4 vertically. Okay? Alright, so now we're going to calculate this unit vector. So the first thing I want you to do is I want you to visualize this. Okay? So let's just think about what this vector V looks like. So we have 3 horizontally and then 4 vertically. So it's like this is vector V. Okay? Now, the first thing you want to do is you want to find, I'll wait till you draw this. Okay, so the first thing you want to do is you want to find the magnitude. You want to know the length of this vector that's been given, okay? Because we're trying to force it to have a magnitude of 1, a length of 1. So right now we should know what kind of length it has. So we're going to find the magnitude first. So to find the magnitude, what do? So square root of 3 squared plus 4 squared. That's all you do, right? So that gives us, what, 25, square root of 25. So this vector has a length of 5. Okay, so the magnitude of V is equal to 5. So that means that the length of this vector right here is 5. Okay, what we're trying to do is find the unit vector. So we're trying to force this vector to now have a length of 1. So doesn't that mean it's got to be like 1/5 of the length if this is going to be the unit vector? Right? It's still going in the same direction. We don't want to change the direction. We just want to change the length. So now this represents our unit vector. So in order to find the unit vector, to force that distance of 1, you're going to take 1 over the magnitude of V. So we're going to take 1/5, because don't we want 1/5 of the length? And we're going to multiply it through as a scalar of 3, 4. So now when you do that, when you distribute, you have 3/5 and 4/5. So the unit vector for V is 3/5, 4/5. Now, if you don't believe me, we can check it. Let's find the magnitude of this unit vector. So if I find the magnitude, I just have to do 3/5 squared plus 4/5 squared. And if I'm right, if this is really the unit vector, what will my answer be? 1. So what's 3/5 squared? 9/25. What's 4/5 squared? 16/25. What's 9 plus 16? 25 divided by 25 is the square root of 1. The square root of 1 is 1. So it checks out. Okay, so that's a good check you could do if you're not sure if you found the unit vector right. Notice it still has the same direction. I haven't changed that. Okay, you just have now counted over 3/5 and 4/5. Again, my picture isn't drawn very accurately, but that's okay. You get the idea. Do we need to do another one of these? I don't think so. Right? Okay, we're done.